So good morning, everyone. I'm Andrea Petrocchi, PhD student at the University of Glasgow. And today I'd be talking about what I found during these 3 years at the University of Glasgow under the supervision of George Barakos in a presentation titled Numerical Study of Unsteady Separated Flows. So the main topic of my research is transonic buffet. This is a mechanism consisting of self-sustained shock oscillation around airfoils and wings in transonic regime. So we want to study transonic buffet for several reasons, mainly because we still don't know what drives this kind of oscillation on transonic aircraft. Moreover, from an industrial point of view, it's quite annoying, dangerous, as it can bring some detrimental effects. And that's the reason why in a design phase, we want to introduce some buffet boundary within the regular flight envelope of an aircraft. And so the second thing we want to look at is onset prediction method. Unfortunately, due to gusts or emergency maneuvers, sometimes we can cross the buffet boundary, and so buffet occurs. And that's the reason why, a large variety of works have been devoted to study flow control for this case. So during this presentation, I'm mainly gonna cover this kind of three topics, meaning we want to understand, predict, and control buffet. And as I said, in this presentation, I'm not gonna go too much in detail about the mathematical modeling because it might be too long. But I'm trying just gonna jump to the results that I obtained during these 3 years. So the first part is devoted to understanding, as I said, buffet, and we're going to do it by using time marching simulation. The method we want to use is a partially averaged Navier-Stokes approach, PANS, that I'm going to describe briefly. So this model is a bridging model between RANS and DNS, for which couple parameters, that is usually used in conjunction with some two equation at viscosity models, such K epsilon, K omega. And by defining a couple parameters here, Fk and F epsilon or F omega, that are then resolved to total ratios of turbulent quantities, we can actually locally reduce the eddy viscosity with respect to the RANS value. And by doing this, we can actually unlock flow instabilities. So usually the main character of this method is Fk, and as Fk reduces, we are able to resolve many more structure and many more turbulent content. So if Fk tends to 0, we are forgetting about that viscosity, while if Fk tends to 1, we are actually using a RANS modeling. And here in this work, we applied the PANS model to the K omega, the PANS pro to the K omega SST model, and what actually have is it's nothing but a modification of all of the terms in the two equation model of Mentor, and that I easily implemented in our code HMV3. So now we jump to the results. The test case that I've used is the OAT airfoil studied in 2009 at ONERA. And for our simulation, we decided to account for the experimental wind tunnel that is sketched here on the left. And to cut costs associated with the simulation, we just modeled half of the computational domain by using symmetry boundary conditioners, and all of the other boundary conditions are follow this color code on the left. This is the computation has been performed in using our solver HMV3. That is a multi-block structure solver. And here on the right, you can see a glimpse of the mesh that we have used, and also the numerical information about numerical stuff. So now I'll speak a little bit about PANS and how do we estimate Fk. We would like to have a dynamic evaluation of this parameter that allows us, that adapts to the instantaneous shock position, and also to the local level of turbulence. And by using this, to do this, we used couple of estimates that are popular in literature, and we compared their performance. In particular, we opted for the second one because the first one has a coefficient that must be tuned, so it's not practical from a computational point of view. And what we would like to have, and what actually we obtain, is to have Fk values close to 1 in the touch boundary layer, meaning we are still using the RANS modeling, and then smaller values in the outside of the boundary layer or in the separated boundary layer, where we want to move to scale resolving mode. And so the results for the pre-buffet case actually already tell us what's the challenge of this case. In particular, the addition of sidewalls result in a large corner flow separation here, and also the shock front that you can see from the earth flow visualization and the friction lines is not uniform and bends toward the sidewall. And here the results in terms of pressure distribution that we obtained are not spot on, but still the agreement is quite fair. Moving to the buffet case, you can see how now the pressure distribution is mirrored, and we tested the ability of pans to work with different grades. And as you can see, we were able to predict buffet for different meshes, while with the Urans by using the Urans SSD model, we weren't able to predict buffet. So this is already an improvement. And if you look at the difference in the Q criterion here between different meshes, you can see that by using a final discretization, especially in the span-wise direction, we are able to detect some large structure that I'll explain in a second. Indeed, coming to the 3D buffet dynamics, we see the presence of this large, I would say, mushroom shaped structure. And I'll try to characterize a buffet period by explaining what happens by means of friction lines. As the shock approaches its most downstream position, intensifies, and two separated flow regions are generated, one at the trailing edge, the other at the shock foot. As they merge in a fully separated boundary layer, there are some vertical structures that here are created at the interface between the fully separated boundary layer and a region of attached flow. And this structure that are created close to the sidewall propagate towards this, the center of the experimental tunnel on the wind tunnel facility, and they develop into large 3D cells that have an effect on the shock front that becomes not uniform, and they push the shock upstream. Once the shock reaches its most upstream position, the boundary layer reattaches, and a new buffet period can start. And this to me is quite interesting, because we've seen in the literature that 2D and 3D buffet, I'll say, develops under different patterns, and this is kind of in between. We can interpret this as a bridging between 2D buffet that only sees the presence of boundary layer separation and reattachment, and buffet cells that develop for 3D archive configuration. And in this case, we can see also that the numerical, that let's say, quantitatively, we are able through pans to predict the flow topology that was observed in the experiment. Even from a quantitative point of view, we are almost there. And surprisingly enough, when you look at the 3D spectral analysis, we can see that, okay, in the chordwise position, we still have a region with high energetic content that is corresponding to the shock excursion. But when we look at the span-wise distribution, in spite of the large structure that we observed, the spectral content is pretty much invariant, and it is something that was already studied in the experimental campaign. And this leaves us with a lot of questions that we would like to answer in the near future. So, to just wrap up on the first part, we can see that pans improved the results of Urans, and we're able to mainly observe a strong 3D component of the buffet flow in our wind tunnel, in the wind tunnel. And so what I'm going to do later on is I'm gonna further study pans and apply it to a pool of test cases to provide guidelines for the use of this method for an industrial and practice from an industrial point of view. So now it would be nice to use pans to study the buffet onset for let's say industrial configuration and large cases. Unfortunately, time machine simulation can be quite expensive. And that's the reason why we need something fast to predict buffet when it comes to the design phase of an aircraft, for example. And that's what people has done so far. I mean, they use runs-based criteria that are based on either local quantities like pressure, trailing edge divergence, or global quantities like aerodynamic coefficient, CL or CM. And what they usually do is they determine a linear regime, and once these quantities deviate from it, we can say, okay, we have buffet onset. So these are the results we obtained for two different criteria on lift coefficient and moment coefficient for two configuration with available experimental data. And you can see that there is kind of a difference between the two, although both of them are conservative in the meaning that in the sense that they don't overestimate Buffett. That's good from an industrial point of view. So what you've done, and I'm not going to go into detail because it would take a lot of time. We have formulated an algorithm based on the joint method to estimate derivatives of the aerodynamic coefficient with respect to the flow condition. And by doing this, we formulated an algorithm to replicate the results of the runs-based criteria. And if you wanna know more, you can read that in the publication on the space and technology that I have with George. And you can see here how for both cases, for the NACA 012 and the OAT15A, we were able to reproduce pretty much accurately the results of runs-based criteria with the CPU time saving that is in the order of 50 to 70%. That is quite good from an industrial point of view. But still, we saw that there's a big difference between different criteria. So we would like to account for the results from time marching simulation that are most probably more accurate in our Buffett onset estimation. And to do this, we use the harmonic balance method. This is a method that assumes the flow as periodic, so it's fine for our case, as Buffett in first approximation can be thought as a periodic flow. And what we do is we do nothing but a Fourier expansion by using a limited number of harmonics. The problem is we can't, we can, but it will be very, very tough to resolve this system of equation in the Fourier space, as it's very difficult to compute the Fourier form of the residual. So we do what all and co-authors did in 2002, and we are happy not to solve the entire flow period, but to have a solution at the selected equi-space point over a period of Buffett or over a flow period. And by doing some tensor multiplication, we can get the harmonic balance computation that is now an algebraic system, and that we usually a linear system that we usually solve by time matching the system of equation. And what we're going to obtain is, as I said, 2n+1 flow solution over a Buffett period. So cool. The problem is we need this quantity that is the fundamental frequency of oscillation for turbo machinery or blade or rotor blades, or cases where it is a design parameter. We're fine because we know it. But for self-induced, I would say, instabilities flows like vortex shedding or Buffett flows, we don't know it. So what I've done is I've implemented a frequency adaptive method in our solver. I'm not going to go again into detail, but I'll provide you with references later on. So now I'll jump to the results. We have studied the laminar cylinder very low Reynolds number to test our method, and then we moved to a couple of Buffett cases. And you can see that the time marching simulation were pretty much able to predict the fundamental frequency correctly, and also from a qualitative point of view. How do we run the harmonic balance computation? The problem is, like, as it involves like a Fourier expansion, we cannot, and we are solving for selected points, we cannot start from initial snapshot that are all the same, because otherwise in the reconstruction we will get a steady state. So in the beginning we need to plunge our cylinder or pitch our airfoil to introduce some perturbation in the computation. Then we can start the harmonic balance computation by using a guess value for the fundamental frequency, and then it's where we can actually use the GBVTP, that is the frequency adaptive method. And at the end of it, we are gonna obtain the flow solution at selected points over a vortex shedding period. And as you can see, as the number of modes retaining the computation increases, the solution gets better and better. And here you can also see how the history of the residual goes as the harmonic balance simulation proceeds. In particular, by using the adaptive frequency method, the residual can be reduced by a satisfactory amount. And okay, this is just a quick display that this adaptive frequency method is pretty much independent of the initial value of the reduced frequency, and also it works well with different kind of harmonics and with different number of harmonics. In particular, as we increase the number of harmonics, the computation tends toward an asymptotic value that would be the experiment, or the one from the time matching simulation. And now we get to Buffet, and you can see pretty much the same plot as the one I showed for the cylinder. And as the number of harmonics increases, the solution gets better and better, and that adheres even more to the time matching simulation. While if you look on the left, we have the comparison between time matching simulation and harmonic balance computations, and you can see that the method predicts quite well the 2D Buffet, in particular the boundary layer separation, area attachment, and the shock motion. Here I show how we actually monitor our computation. In particular, we can evaluate runtime, the aerodynamic coefficient associated with each of the snapshot with each of the time instance, and you can see that in the end the solution is pretty much converged. And here on the bottom right, you see that by using the harmonic balance computation, by increasing number of harmonics, okay, we still have some saving with respect to CPU, in terms of CPU time with respect to time matching simulation, and this decreases, of course, as we increase the number of harmonics. So now we want to use this for a Buffet boundary estimation procedure, and we saw that as we're using an adaptive frequency method, we can actually vary flow condition pretty much dynamically, and the harmonic balance computation will still be able to give us a reliable, an accurate solution. And in this case, by starting from well-developed Buffet, we can lower the angle of attack until the loads associated with the snapshot converge towards a singular value, meaning that we no longer have Buffet. And we developed another algorithm similar to the first one, and for Buffet boundary estimation around the two cases that I showed before. And you can see you can draw some conclusion. In the beginning, we can say that where the underlying turbulence model works well, predicting Buffet, we have an improvement with respect to the runs-based criteria that are at times too conservative. Unfortunately, the problem of harmonic balance is if the underlying turbulence model doesn't work well, of course, the other harmonic balance will not be able to predict Buffet. And that's what happens for the NAGA 0012 at Mach number higher than 7.78. This in literature are not, notoriously difficult point to predict. But we're still happy because in this case, we can still account for the results from time matching simulation at a reduced CPU cost. Now, I provided you with a couple methods to estimate the Buffet boundary, but as I said before, under unfortunate circumstances, we can cross the Buffet boundary. We can undergo these nasty oscillations. And so we need to be able to control Buffet. In the past, several devices have been used to control Buffet. Among them, we see motor generators, trailing edge flaps and devices, and shock control bands. Some of them have introduced yesterday. So some of you have introduced yesterday. Unfortunately, all of them have some disadvantages. They have off-design penalties, installation drag, and difficulty in the implementation. So we thought, why don't we use spoilers that are already there? And why are we thinking about this? Okay, now I'm gonna borrow the acoustic feedback mechanism from Lee. That is pretty much one of the two most accepted theory behind Buffet, and to explain why we want to use spoiler for this configuration. How does it work? When the boundary layer is fully separated, there are some disturbances traveling from the shock foot to the trailing edge. Upon reaching the trailing edge, some other disturbances are scattered back outside of the boundary layer to energize the shock by completing a closed loop that sustains our Buffet. So what we thought is we want to introduce some obstacle here in the boundary layer to prevent the disturbance propagation in the boundary layer. And this is quite convenient because we've seen that in the literature, Buffet usually develops around the mid wingspan, and that is where spoilers are mounted on civil airplanes. To do this, to simulate this device by using CFD, we use virtual surface modeling, meaning that we didn't have to actively mesh the device for all of, by changing parameters every time. And what we do is we actually impose no slip boundary condition at the on the cells that are corresponding to the spoiler position, and that allows us, once we do a nice grid, to change geometrical parameters like the length of the spoiler and the orientation of the spoiler. Of course, this also allows for dynamic deployment that we did, but I'm not going to show you. So, jumping to the results. Here I show the aerodynamic coefficient, in particular I show the lift and drag coefficient. Before, in the in-control case, we have large oscillation of the coefficient, and then when we add control, we can see that even if we deploy with a very small angle our spoiler, the shock oscillation are suppressed. And you can distinguish, I would say, two categories of cases. The cases where the aerodynamic coefficient lay within the uncontrolled, range, the uncontrolled range of them, and there are cases like the pink or the green where the aerodynamic coefficient deviate a lot. And now I'm going to show why it happens. For a small deployment of the spoiler, you can see you can still have two separated flow regions. The one induced by the shock that is strong enough to promote boundary layers, to cause boundary layer separation, and another one created by the fixed point separation here, given by the spoiler. As I said before, the spoiler breaks the separated flow region into two, so it prevents disturbances from traveling in the separated boundary layer, and this is the effect that helps canceling buffer. While if we deploy the spoiler more, we're going to have a fixed point separation region that is quite large. This induces a actual modification of the alpha shape, and culminating in a reduction of the local angle of attack. So the shock moves upstream where it's quite weak and is no longer able to separate the boundary layer. And this can be quantitatively shown in the CP plot for different deployment angles. And as you see, when the spoiler is deployed more, the shock moves upstream and upstream, and this results in a significant drop in lift. While for small spoiler angle, we have a mild increase. That results in a mild increase, unfortunately, in drag. But when we deploy the spoiler even more, it would say it works as a night break. So the orientation with respect to the free stream and the difference in the jump in pressure across the spoiler give an additional contribution in terms of drag. Similar consideration can be done for the moment coefficient, and in particular we have a mild nose up for small angles and a mild nose down for higher angles. So before concluding, I want to show our experiment with the finite device and the differences we have with the 2D case with infinite spoiler. And you can see here how there is a strong flow three-dimensionality that is promoted by the presence of a finite spoiler with a compression here where when the deployment angle is large enough. And in terms of CP around the airfoil, you can see that the pressure jump is quite reduced with respect to the 2D case, and this resulted in a difference in a mitigated effect on the aerodynamic coefficient. Yes, and here by means of CFD friction line, you can see how the presence of the spoiler forces the flow to just go around, and also introduces a strong flow dimensionality that is actually visible in the CP distribution. Now, I think it's everything for me. Just to wrap up, we saw that spoiler effective for buffet cases, and the method that we've used allowed us a certain flexibility for studying the problem by using different geometrical parameters, and that the addition of, the comparison with the 3D told us that the effect is actually quite reduced with respect to the infinite devices. And now the next step will be to apply this to proper 3D transonic winds, where we know that Buffet is developing, under slightly different through a slightly different mechanism that involves Buffet cells and cross flow with the propagation in span. So this is what I'm probably gonna do later. I think that's everything from my side. I hope you enjoyed the presentation. If you have any question, just ask.
Thank you very much, Andrea. Very interesting talk.